lecture now we are going to see majorly about computational fluid dynamics. Okay. For that one, so computational methods we are going to see. One of the method I have chosen is this finite volume method. Okay. So my aim of this lecture and the next lecture is to show you the outline or method behind, what is the methodology behind this finite volume method, followed by we will go to the lab and we will do some problems using MATLAB. Okay. So the basic equations whatever we are seeing for the past 4 days, I think, isn't it? Today is the 4th day. 4 days, those governing equations, okay, that is Navier-Stokes equations, continuity equation and heat equation. Okay, along with the rotation also we are seeing, isn't it? Yeah. So before that one, I want to show you the simple, starts with the diffusion equation, our Laplace equation, both steady and unsteady. Then we will add the nonlinear term, convection diffusion equation, then convection diffusion equation along with the pressure field. So how many unknowns are there? Only if I consider Navier-Stokes equation, you have velocity, 3 components are there, then pressure is there. So 4, isn't it? We have equation of continuity and Navier-Stokes equation. Along each component we have one equation, U, V, W. Then this continuity equation. So 4 equations, 4 unknowns. So how to solve them and get the dependent variables U, V, W and pressure also using simple algorithm. Simple means semi-implicit pressure linked equations. That is given by one of the professor in IIT Kanpur. Okay, yeah, IIT Kanpur. Of course, okay. So this finite volume method only I have used to simulate the blood flow and this corrosion problems. Okay, and the ship hull, that is backward facing step. Okay. So these are the applications, and one of the application now professor is talking on this one. So that one I want to show you, this one. So here the plane layer, that is top is one plate and the bottom is another plate. Bottom plate is getting heated up, that's why this red color is shown here, and the top plate is cool. That is what it is written, top cold wall and isothermally electrically conducting one. Similarly bottom hot wall. So there is a temperature difference here, and the liquid is gallium. Here it is filled with gallium, but we are seeing that our earth is composed of liquid iron mostly. But here why I have chosen gallium is because experimental results are available. Some Arno and Olsen, they have done the experiments for this geometry, set of geometry. So using finite volume method we have simulated and we compared with that one. That is the idea behind that one. And apart from that, it is this geometry is kept in the vertical magnetic field. At the end, rotation also given. Okay, so heating, magnetic field and rotation. These are the things. Okay, so I want to show you that one, how it will look like. So these are the properties. From where we have taken is from that paper Arno and Olsen. What is the liquid gallium density? You can see here, isn't it? And that melting temperature, all this stuff. So whichever you are giving in these Navier-Stokes equations, day before yesterday, I think you have non-dimensionalized the equations. In that one, you would have seen all these quantities. Okay. Then, yeah, these are the equations. First one, I think you are familiar, na? This one, continuity equation, divergence of velocity vector is 0. Then induction equation, divergence of magnetic field. Then this is our Navier-Stokes equation. Okay, so this is our unsteady term. Then this is our nonlinear term. Then here comes magnetic field effect. Okay, then here comes the pressure term. Then again here, okay, we are non-dimensionalized this one. This is a Coriolis force, T is the Taylor's number, then Laplace term, then here temperature effect. Then here is a heat equation and magnetic field equation. So we are going to solve these equations to get the values. So okay, I will show you the results, what we have got that one. Yeah, here as I said before, you can see very well that shorten this. Yeah. See, the left side is the temperature difference. That is the temperature difference between the bottom plate and the top plate. If it, how it is changing with respect to the Rayleigh number. So, you come across about that Rayleigh number in the non-dimensionalization. Rayleigh number multiplied by Prandtl number. RAPR. That is a task 1, I think. We are sitting here and we are non-dimensionalizing. You also come across about that Rayleigh number and PR. Prandtl number. Okay. So, these are the experimental results of Arnia-Olsen 2001 published in Journal of Fluid Mechanics. So, we compared with that with the simulations. It cannot exactly match with this because there also some of the assumptions are there in computations, also some of the assumptions are there, round offs are there. Okay. So, this is the one. Yeah, here you can see the convection and convection. When the heating is less, that is the temperature difference between the bottom plate and the top plate is less. Parallel lines you can see here. So, the temperature moves in this way from bottom to top. As I increase this one, you can see how they are moving. Okay. So, convection starts. This is what madam said about that onset. Can you recollect the word onset? She said when it occurs, when the convection to convection occurs. So, this value exactly 1275, our Subramaniam Chandrasekhar book also, they calculated analytically and shown this value. Okay. When 1708, I think, isn't it? 1708. It is not 1275, 1708. When Rayleigh number is 1708, you can see that this heat transfer rate will be greater than 1. That means convection starts. Below that, it will be conduction state only. Convection means movement of fluid particles will be there. Okay. Yeah. And then these are nothing but the our velocities, u, v, w, like that. Okay. So, these are nothing but our streamlines. Yeah. Some of these structures, why we have to go for the three-dimensional solution of the equations. If I cut the plane, you will see the two-dimensional one, but the same thing is visualized in the 3D way. In the 3D way, you can see that somewhat bending structures. They are known as cylindrical sneaking structures. Technically, they known as. Why I am showing this figure is, usually if you go for the 3D visualization, you will get more depth analysis. Okay. But today, we are going to do 1D only. We are going to start with 1D only in that method. Okay. Yeah. Okay. Then other thing is this one also. Yeah. Q is known as Chandrasekhar number. Here you can see na Q. Q is known as Chandrasekhar number, and this hall name also Chandrasekhar. Okay. Yeah. So, here you can see the 3D structure. These are nothing but our streamlines only. This occurred exactly the number, the values given by Chandrasekhar. I have tried for some other values also, but results are not converging. I think all of you know about convergence of the results. So, the results are keep on oscillating, but after seeing the book by Chandrasekhar, Hydrodynamic Stability, Hydrodynamic Theory and hydromagnetic stability. In that book, he has given this number. So, I put that values and solved that equations using finite volume method. We got this one. Okay. Okay, then let us final one. Yeah, final one is here. Rayleigh number not equal to 0. That is heat is given. Here magnetic field is there and rotation also there. Taylor number. 3 things are taken up in that one. So, the title also shown. Okay. Some analysis has been done. You can see very well that it is a rotation. The streamlines are shown in this way, and the heat also getting disturbed here. This is what I have shown here. Okay. So, let us move on to one of the application only I have showed for finite volume method. Basically, method we are taking, we are applying in the different fields. Yeah. So I don't want to go very deep into this one. Simply I have written what we have to do is select a real world problem, and now we are selecting this geophysical astrophysical problem. Then formulate the flow problem. That means mathematical model is nothing but our equations. Simplify the model without loss of physics. So many simplifications we are doing. Even we are seeing na Rossby number, Ekman number, they are very small. So that terms we are omitting. Okay. So, but yeah, because it is 10 to the power of minus 15. That's why we are omitting. But still, keep it and solve the equations. How that behavior is there. Decide about the computational domain. Where you want to solve that one. Whether you want to solve the previous one I showed in the planar layer. That is rectangular. No, not rectangular one. In a box, isn't it? It's not cube also. Okay, then but professor is telling about the spherical one, the sphere. So you have to decide about your domain also. Then discretize the geometry, generate the grid. Grid lines you have to draw in that one. At the grid points we are solving the equations. Then discretize the equations using finite difference method, finite element method, or finite volume method. Finite volume method or finite element method, boundary element method. So many methods are there. Whichever method you want to, you can take. Okay, specify the initial and boundary conditions. Then only closure of the problem will be there. Set up the CFD simulation. This is the known as post processing. This is pre-processing. Then comes here solver. So any software if you take, it will have three components. One is pre-processing, solver, post-processing. In the pre-processing, all these things will be done. Which equations, everything, okay, computational domain, generation of grid, up to this. Then this blue color one is solver, we call it. Then comes the solver is containing both discretize the equation, specification of the initial and boundary conditions. Then this CFD simulation, here onwards it is analyzing the results. We used to call in the papers results and discussion. So those things comes into picture here. Okay. Yeah, these many softwares use the finite volume method. Yeah, see the revenue. This one I prepared when, I don't know, before 5 years I think. This much revenue they are earning. Okay. Now let us move on. Okay. Yeah. This one I said. So if we choose any method, it should have these qualities. The solution must exist. If it exists also, whether it is unique or, yeah, that one also we have to take care. So another one is a small perturbation in the approximate solution should not result in large change in the result. But it changes because we are dealing with the nonlinear equations. Okay. If I take my initial velocity as 0, instead of 0, if I consider 0.10 to the power of minus 5, then my solution should not change. For 0 and 10 to the power of minus 5. If it changes, yeah, definitely there is some effect. That is what small perturbations. Even you should take 10 to the power of something also. We have simulated such type of problems also. Okay. Then convergent. We need the converged results. Discrete solution tends to the exact solution as the grid spacing tends to 0. When the grid spacing means delta x, we call delta x, delta y, delta z. If they are very small, this numerical solution should go match with the exact solution. Exact means analytical solution or experimental solution. The next one is consistent. Truncation error becomes 0 when the mesh is refined because we are discretizing. Basically we are applying the Taylor series. We are neglecting the higher order terms. That's what it is written here. When the mesh is refined, okay, delta x based on that. Then we should have a stable. Numerical solution must be bounded and the errors must not be large. As we keep on increasing, we proceed with the time, the error should not increase. Okay, that is also one of the criteria. So all these things should be satisfied. Convergent solutions, consistent solutions and stable solutions. Okay, now let us coming to our topic, finite volume method. Solving the partial differential equations that calculates the values of the conserved variables. Here conserved variables, if I take Navier-Stokes equation, velocity, pressure, okay, across the volume. Advantage of FEM over FDM is that does not require a structured mesh. In unstructured mesh also it performs well. But if you go for the even finite difference also, we can use unstructured mesh, but it is more easy to implement here. Okay. Finite volume method is preferable in comparison to other methods as a result of the fact that boundary conditions can be applied non-inversely. We are going to see a separate 2-3 slides only for the boundary conditions, how to apply here. This is true because the values of the conserved variables are located within the volume element. This is what C dot V it is written. This is known as control volume. Okay, this is control volume, and not at the nodes or surfaces, not at the mesh points or grid points. Okay, inside the control volume. Yeah, so non-uniform grids already I said na, unstructured mesh. So what this tells is whatever comes in it should go out. That is why we are calling it as a conserved variable. Inside the control volume nothing should stay. Okay, that is the idea behind this one. Let us see how we are applying this one in the methods. Okay, so again and again we are going back to the equation. Instead of phi, here rho is the density, t is the time. Phi can be anything. Phi can be any dependent variable like velocity, temperature, magnetic field, okay, electric field, that equation. So this one, and here comes our nonlinear term. So phi is the unknown dependent variable. Okay, in my wordings, phi is the dependent variable, v is the velocity. Then here this side we have diffusion coefficient. If gamma is a constant, it will come out. This divergence of del is del square phi. Okay, then comes the source term. It can be temperature in the Navier-Stokes equation. Otherwise, if you go to heat equation, another terms can be there. So S is known as the source term. So this is the general form of the equation. Now we are going to discretize this equation and we are going to solve this one. So here comes the unsteady term, nonlinear term or convection term, then diffusion term. Gamma is known as the diffusion coefficient. Okay, then source term. So these are the parts. That's what written here. I think I can use this itself. Yeah, no need to go there. So all equations are written here. Okay, let us start with the diffusion equation. Okay, steady diffusion equation. That means it is time independent. Yeah, here is the equation is shown here. So equation number 1 is here na. So if k is a constant, simply it will come out. So now let us understand this grid, how we are placing this one. Usually we call P as I minus 1, I plus 1. That is a notation we come across already. Instead of I minus 1, I plus 1, we are using here P, W and E. West side and east side, that's it. Okay, so our control volume lies in between this. Control volume sizes we are taking as delta x. Okay, and then yeah, here this P to W, it is written in this notation, that's it. That means this delta x need not be equal to this delta x. Here itself we are seeing the unstructured grids. Okay, I think it's clear. From here only we are going to start. I means I minus 1, I plus 1 is there. The distance between I and I minus 1, distance between I and I plus 1. Instead of telling like that, we are calling it as WE. If I denote with small w and e, it is about the control volume. If it is with capital W, capital P, etc., it is for the grid points. Okay, that is the thing. Next one. Yeah, this is what it is written. Now, what we are going to do here is we are going to integrate that equation over this one. Integrate this equation from W to E. I minus 1 to I plus 1. Okay, that is what we are doing. Both sides. Here also integration, here also integration, because it is a 1D integration with respect to x. Okay, so what it will be here, isn't it? East minus west. Upper point minus lower one. And here you can see now the second one. W to E, this is what written. The second integral due to the source term in equation 2 is evaluated by assuming that the integral is locally constant within each control volume. Okay. Now, how to do this one? Partial with the derivative of t with respect to x. Okay. Yeah, that is what it is written. So, what is that? Partial derivative with respect to e. E means how it is located here, this point. Okay, partial derivative with respect to e. This one we want to write down. So, that derivative is written with respect to this te minus tp divided by the distance between them. If you want, I will write down, or you can also note down. You see here, te minus tp divided by distance between them. Similarly, this also. Why you are thinking it is, isn't it? Same thing, whatever there, I am going to write down. This side we have integral of differentiating with respect to dx from w to a. This is what written here. Okay, only one term. Yeah, this to this multiplied by delta x. Okay, the distance between them. So how to write down that one? This figure also we have, no? Okay. This is W. This is our control volume. Okay, we are integrating from W to E. This one. That is what it is written here. So this one is written there as using this and this, because we know the values at this capital P, capital E. So the distance between them is, that is what written there. Okay. For the next integral also same thing. This one is like this. This is the notation only. So now everything is collected and we have written here. Let us for time being, S is written as SC plus SP into TP. It is rewritten in this way. You see here, average value of S over the control volume. Now we are collecting this term and we are writing. This is only the collection of terms. So this is the coefficients of T at the point P equals to coefficients of T at the point E, then at the W. So this one coefficients, we want to know the value at this one with the help of neighboring points. Usually we call it as I minus 1, I plus 1. We want to know the value at I using the values at I minus 1, I plus 1. Okay, that is what written there. Now we are getting the tridiagonal form. If you write down the system of equations, then you will get the tridiagonal form. That is I minus 1, I plus 1. That is what written there. So every coefficient is written there. The beauty is here. What is that is? Now you can rewrite them easily. This one, whatever coefficients are there, that is what it is written. Now this coefficient is a combination of the previous one and the next one. Here whatever value you are getting here, that is what written here. Okay, then minus whatever we are going to get, this one. So this is what, so totally what it is telling is this one equals to the neighboring one. Sum of all the NB means neighboring values. That is what, no, I minus 1, I plus 1, no? The neighboring ones plus this coefficient. So what is the property we can see here is it should be diagonally dominant. That property also it should get satisfied. Automatically this will be getting satisfied for the diagonal dominance. of the matrix. This one will lead to a tridiagonal matrix and it will be diagonally dominant. Okay. Yeah, then let us understand a little bit about this source term linearization. In which way we have to consider this? So if I have S bar is this form, then I can rewrite this one such that it should be written in this form with this point should be less than 0. We are rearranging only, it will not come automatically. We are rearranging such that this S bar can be written like this, SC plus SP into the value at this point. The value at this point, it should be, the coefficient should be less than 0. The previous slide I showed the coefficients, no? This AP, AE, AW, etc. This coefficient should be less than 0. We are rearranging, that's it. Okay. Yeah, so many examples are given here. Let us, yeah, this is what you see here. It will be consistency at a control volume phase. So, whatever comes in, it must go out. When a phase is common to two adjacent control volumes, here we have a control volume. This is one control volume. Another control volume will be here. Again, I can take I here, I minus 1, I plus 1. So, that is what it is done. The flux across, it must be represented by the same expression in the discretized equations for two control volumes. Whatever flux we are taking, the derivatives here, flux must be represented in the same way for each control volume. So, the positive coefficients here, all coefficients, that is AP, must always be positive. If we are doing any mistakes, automatically it will be known there. Negative slope linearization, this is what just now we have seen. It should be less than 0. Sum of the neighboring coefficients, AP equals to sum of the neighboring coefficients. Okay. Now, coming to the boundary conditions, this is another important one, how we can deal the neighboring coefficient. Just now we have seen about this one only. P and west and east point, typical control volume. Now, coming to the boundary point. Okay. Here, how we can deal that one, that is what shown here. See, this dotted line denotes the control volume. Yeah, dotted line denotes the control volume and it matches with the boundary points. So, if I take here, for example, again, something I should. So, if I take one more, yeah, here again, if I take one more control volume, it will be like this, around this W. Okay, but my boundary will end here. Boundary point will be ending here. So, the distance between these 2 points, if I take, it should be delta x by 2. That is what it is written here. Delta x by 2 is written here. Okay. From this to this, the distance between them is delta x by 2. So, if I discretize this one, dou t by dou x, here I should write down it as ti minus tb divided by delta x by 2. Okay, the distance between these two only I will write down. Confusing. Where it is written. Yeah, that's what we have to take care. While we are doing the problem, we will take care. Same thing is applicable for this side also. When you are dealing with the boundary points, you have to take care delta x by 2. What is the meaning of that one is, the control volume is situated in between two nodal points. Capital W, capital P is there and this is the control volume. Yeah. Again, we are repeating the same thing, over relaxation and under relaxation. That means whenever we get oscillations in the solution, how to control that? That is based on over relaxation and under relaxation method. In numerical methods, we would have come across about SOR, successive over relaxation. Have you heard or not? No? Successive over relaxation, successive under relaxation also there. The same knowledge only applied here. How to use the previous one and the current one. Okay. To find out the current value. Okay. To find out, we want to calculate the temperature at the point P. So we have the previous iterated value also and current iterated value also. How much we should consider? Based on alpha value, you can consider that. Whether if I put this alpha equals to 1, so what will happen here? Both will get cancelled out. So only the current value is in, this is a current one. You will take the current one. If alpha equals to half, so the previous one values, previous iterated values, half of that you will take. Current value you will take half. Okay, so this based on this alpha value we are considering that. Yeah, convergence criteria. Already we come across about the convergence criteria. We are going to specify that. This is the equation and the residue we are writing here. Okay, how we are writing? The value of this is nothing but our conserved variable or temperature, velocity, some variable value is here minus the previous one. The difference between the previous iteration and the current iteration should converge to a certain limit, whatever we specify. Okay, so now with that we are going to add time also. Previously we have not added time. Now we are going to add the time. Okay, yeah, you see here. This is what we have seen. Along with the source term we have seen. Now we are adding the time. That means integration is also W to E and T to T plus delta T. Okay, that's it. T to T plus delta T we are adding. The same thing, na? Here also this term is there and it is a one-dimensional equation. So now how we are doing this one? You see here. The only this term is taken up here. Rho C delta X. This next iteration minus current iteration divided by delta T will come here, isn't it? Delta T will be there and yeah, it will go to that side, I think. Yeah. Here is the delta T, you see. This one. T to T plus delta T, Tp delta T is like this. If F equals to 1, what will happen? If F equals to 1, then this will not be there, current value. If F equals to 0.5, it is the average of the previous one and current one. Like that it is written. F is known as the weighting factor between 0 to 1. So this it is given here. So how we are rewriting this one-dimensional heat conduction equation. This is the final form. Already we have come across about this one, the square brackets one, from the previous diffusion equation, conduction equation. Everything is said. Now we have the additional term of time. Time is denoted with respect to n plus 1 and n. Okay. For this we are going to write the code, MATLAB code. Okay. Yeah. So how much F we have to choose? F equal to 0 means explicit scheme. F equals to 0.5 means implicit scheme. In that also 0.5 means Crank-Nicholson scheme. If F equals to 1 is fully implicit scheme. They are unconditionally stable. The beginning I showed, na, the method should be stable. Okay. Yeah. How we are finding out this one? We have to choose our mesh size of time such that it should satisfy this condition. This is known as CFL condition. Okay. How much we have to choose means here this is a constant. So rho C and K are constants and delta X is the mesh size which we are specifying along the X direction. Okay. Yeah. So this is fully implicit discretization scheme and these are the coefficients are given here like the previous one. Yeah, convection diffusion. Now comes the main part of nonlinearity. Nonlinearity. Previous one, first one is without anything, only diffusion term. Okay. Second one is with time derivative. Now comes this one with the, already we have done this right hand side. Instead of phi, we have written here t. Okay. And this left hand side is the nonlinear term. So, for u also unknown and phi also unknown. If u is known, it is known as quasi-linearization. We will move step by step, okay? By thinking that U is known to me, rho is a constant we take, density, U is unknown to me, then we have to solve this equation for phi. Phi can be anything, velocity, temperature or magnetic field, anything, okay? Let us see how they are doing this one. So again, integrating both sides. Integrating from this W to E. Same way only, like this integration. That is why it is written like this. You see there. Yeah, where this is going? I don't know. Oh yeah, it is here. E minus W. Okay. Upper one minus the lower value. Same thing only. E minus W here. That is what. Both sides you will get delta x one dimensional. Now it gets cancelled out. That is written in the whatever we have seen in the beginning. The same picture only here. P is here, W and E, and the control volume is situated in between this, and the distance between them is delta x. Nodal points. Okay. Yeah. Now let us understand the convection term. How it is written. Now what is our aim? We want to find out that phi E and phi W over the control volume. So how we are finding out phi E and phi W? At this point I want to find out the value of phi, and here also at this point I want to find out the value of phi. So simply what they are doing, average of these two values. Phi E equals to because at the nodal points I know the values. At this point I know, at this point I know, at capital W I know. Okay. No work is here, isn't it? Average of these two. But oscillations are coming. Solutions will not converge. Similarly, at this point, if I want, what should I do? Small w equals to that is what shown in the next slide. You see there? First line, na? Convection term. It's written average of these 2 points. Phi is like that, and then phi w is written like this. So I am substituting there and rewriting the equation like before. Substituting them where? In this one. Here instead of u, rho u, e multiplied by this one. You see here? This one. Rho u at e, this one. Similarly, we are writing this one. Coming to this one, same, whatever we have discussed before. Instead of t, we have there phi. Okay. And we are giving some names for this. For this one, rho u, we are giving it as F. F means flux. Here, gamma is there, so we are calling it as diffusion. F and D. There is a relation between these two terms. Okay. That's what we are going to see here. F indicates the strength of convection. Strength of convection or the flow, while D denotes the diffusion. Okay. D always remains positive. Diffusion means how the fluid is spreading in all direction. Flux means only one way. So one way coordinate also we are going to see. This is one of the idea in the finite volume. We are using that one. Okay. Yeah. F can take either positive or negative values depending on the direction of the fluid flow. Because here it is denoted as U. U is the velocity. If I say velocity can be, it can be in the positive direction. Fluid can move in this way also. Otherwise, it can reverse also sometimes. It will move like this. So now here U is positive. Here U will become negative. Okay. That is why flux can be, F can be in the positive direction or F can be in the negative direction. Okay. Yeah. Now he is giving this names for this. AE, AP, AW are there. It is written in terms of D and F, the coefficients, combination. Okay. Since by continuity FE equals to FW. Why? Because that's divergence of velocity vector is 0. Already we have seen that is a continuity equation. starting one. Here, I should go searching. Here, this one. If rho is a constant, if we assume rho is a constant, simply we have here dot should be there. This missing. Okay, del dot. Yeah, divergence of phi bar equals to 0. Based on that, we are writing that. Okay. Maybe I think I will stop. We will work out this one in the lab. Okay. Yeah, this one. So because of that property, simply that coefficient AP is the neighboring points means AE and AW only. Okay. So the writing such type of thing like this is known as the central difference scheme. Name of this one is central difference scheme. But there are different ways how to find out this phi E and phi W. Okay. We will do these things. Yeah. Once you, yeah. This is the main thing. After finishing this, I want to explain this. After finishing those things, whatever we have seen are 2 problems. Those things let us finish in the lab. Then we will move on to here. There also projector is there. I will project the slides. Yeah, that will be better, I think. Okay, now we move to the lab. Huh? Yes. Okay. Any doubts in this? So there, let me know. Otherwise, we go there and solve those 2 problems. Already problems are also different. Here we have the problems. Yeah, this example. This example 1. Consider the problem of this heat conduction in an insulated rod with whose cells are maintained at constant temperature. 500 degrees Celsius. Okay, so of course it will move from temperature, will move from top to here. This one. The one-dimensional problem is sketched in this figure, governed by this equation. Now what we have to do, if I want to apply the finite volume method, I have to integrate this. This one only, this step. This step we have to do and find out this. K is given to be, K is a constant, na? It is given here. Conductivity K equals to 1000 watts per meter per Kelvin. Cross-sectional area is the delta X we have to multiply. That area is given to be 10 into 10 to the power of minus 3 meter squares. Okay, we will solve this one and we will draw the graph also. How that temperature distribution is taking place in this one-dimensional rod. And then if then we will add one more term here, source term, like that. We will add for that problem and we will do this. This is solution of that problem only. Second problem, yeah, this is a solution. There, this graph only, we are going to get that. Yeah, okay, only one problem I did here. This one. Okay, we'll move there. I'll show them there so that you note down and by the side we write the code. Okay.